Hi everybody, my name is Xiangyu Xu, and my advisor is Eric Dan. Today I'm going to introduce discrete Laplace operator is an estimation for dynamic 3D reconstruction. First, I'm going to introduce the problem of dynamic 3D reconstruction. Problem is trying to recover a 3D structure of dynamic objects, which is observed by multiple independent image streams. Like in this graph, like in this image, multiple people record some dynamic objects by their cell phone, and we're trying to reconstruct by those 2D observation. And the challenge is for the static point, you can reconstruct by simply by the triangulation of the viewing arrays. Since it can observe by multiple cameras and the 3D position is not changing. But for the dynamic point, it basically each time is equivalent to the 3D point. At each time, it's only observed by one camera. So it's a problem to reconstruct this 3D things from monocular image, which is impossible without any prior assumption. And some methods use synchronized camera, which will be a problem. So at each time, the structure can be observed by multiple cameras. So you can use the method of triangulation to solve this problem. But in most cases, the camera is not synchronized, so it will be a really hard problem to solve since at each time the structure can only observe by one camera. That's what problem we're going to solve. The outline talk gonna do today gonna related to I'm gonna talk three related work, and finally our own method to solve this problem. First paper is called Generic Trajectory Prior for Non-Rigid Reconstructions. In this paper, they present the 3D structure based on some general trajectory prior, and then they analyze the reconstructability of their system based on the rank of their prior matrix. Finally, they use high-pass filters to avoid the ill-conditioned system. And first, I'm going to introduce some formulation. The first is called a projection system of projection. It's based on the equation that using the project matrix, they project the 3D structure into the 2D image. It's supposed to be close to the 2D observation, and then they reform this equation into a linear equation for the structure X, which is Qx equal to U, and then they try to present the X structure as using a trajectory basis, where here Z is the basis and gamma, beta. Use the coefficient to linear combination of the basis to present the structure, and then they put this X, which is presented by the trajectory basis, into the system projection. Finally, trying to minimize the difference of left side and right side. By this, trying to get the structure. And they trying to transfer this this cost function into in their general trajectory prior form. First, since the X is based on the linear combination of this trajectory basis space, and here this is the non-space of the trajectory basis space. So that means the x suppose don't have any projection. The projection of x to this space is supposed to be 0, since it's perfectly expressed by the trajectory basis. And he replaced this. He changed the cost function and the constraints, which means optimize the x, the projection of x on the null space of this null space, subject to the reprojection constraints. And based on that, he trying to analyze the reconstructability. Here this x prime is the ground truth. Supposed to be, he assume this is a ground truth x, which will certify the projection system. And this Q, this one is the null space of Q, which means plus some component on this space, and this x will still certify this linear equation, since this is a null space and product. Since this is a null space and product is still will be product Q still will be 0. So their conclusion about the reconstructability is, when this null space and the intersection of the trajectory basis, if they have a very big intersection, that means based on the trajectory basis, there will be there will be a lot of part that in the null space of the Q, which actually is the, since this is ground truth, this is our result, will be the reconstruction error. And with more trajectory basis, the number of trajectory basis is more. With the use k, there are more possibility they have bigger intersection. The most simple example here is, since if this is one camera and this is the 3D point, and the null space for this camera is supposed to be the direction along this ray. Since if this point move on this ray, it won't change the reprojection. And if the trajectory basis have component along this direction, the reconstruction may have a large error. And here is there do some experiment by changing the number of the trajectory basis. If the conclusion is, if the trajectory is the number of k is too small, the trajectory basis will poorly represent the structure. But if it's too big, as the analyst said, it will have a very big error. Then they're trying to avoid this yield condition case by implement this high-pass filter instead of the trajectory basis. Actually, instead of their trajectory prior. We here use this G to replace the null space of the trajectory basis. And in their they use two kind of filters, which is -1 1, -2 -1, -1 2 -1. How this work? For example, here is three point in the sequence X, and when implement this -1 to -1 filter is equivalent to find the difference of these two vectors, which actually is the second derivatives, and actually use this -1 1 is trying to present the distance between all neighboring frames, which actually is the first derivative. And the size of this G, since it will apply on every frames, no, every 3D points on every dimension. Also, but for each frames, since like this, it can only apply on which this M is number of the value of the filters, since it can only apply on this plus. I'm actually I'm -1 number of frames, since if the end and start frame cannot apply, since they don't have a previous frame and next frame, and this will be the size the size of the what do you call that? The size of space of G. So the corresponding size of trajectory space will be 3 plus I'm -1, which is a constant value, and I'm supposed to be small if you implement these two filters. So it will not be a yield condition system. Here is some result. He used these two filters separately, and the combination it shows better result than the trajectory basis. And he do some experiment on the real data. In here, the combination, he said if using filter, they have more realistic motion, but actually I didn't see it, but that's what it said. This real data motion don't have ground truth, so you cannot compare the error. And there is the second paper, which called a special temporal bound adjustment for dynamic 3D reconstruction. In this paper, they use some basic physics-based motion prior to constrain 3D dynamic trajectory, and they implement incremental method to jointly optimize for the value of camera parameters, 3D location of static point, and 3D of and also dynamic point, and the temporal alignment between the cameras. Here's some formulation. First one is the reprojection arrow, which is project the X to the camera and cover the arrow, and there's but here the V is the called binary indicator of. This is not clear, so blur. Binary in which means if this point is visible, it's 1. If not, it's 0. And this one is the inverse of the future scale weight, which is the trying to weighting the contribution of this X. For the and here is the motion prior. The least kinetic motion prior, which is so you suppose the mass for each point is the same, so you can drop that part. And he used the distance between neighboring frames divided by the difference time to be approximate velocity, and this width is depends on the uncertainty which introduced below, and also the depth of the 3D depth and schedule of the 3D points. And finally, he combined these two functions, trying to minimize them both, which the cost function will depend on the 3D points. Open this 3D points and the camera parameters and the time offset between cameras. And the relationship of the time offset and the frame over rate, and also the frames is here. Actually, this is frame rate, which actually is known. Sorry, and they do some next they do some experiment to show that their motion prior is good for estimate the time offset in cameras. He set two sequences with different time offset between 0.1 to 0.9 frames, and use these three kind of motion priors. You can see this action have a lot of error, even in the error to the Gaussian error is 0, and the previous to have good performance when the error is small. And finally, in the following experiment, he will use the least kinetic energy prior. And here is their method trying to incremental reconstruction using the cost function. And the first step, he trying to use some initialize of all the value from some geometry triangulation based method. Then the second step, he trying to refine the temporal alignment between all pair of cameras. He used a linear search to try different discrete set of time offset, like the previous experiment from 0.1 to 0.9, and then optimize this function only for the 3D trajectory with the dynamic point, structure of dynamic point, and choose the time offset, the corresponding time offset, and 3D structure with the smallest cost. Then, because the incremental method need to add the camera one by one, so he used next by trying to determine the ordering to add the camera, and he do that to find the minimum spanning tree. So each camera will be a same as a vertex, and the edges weights between each camera depend on this equation. And this Tij, actually T is the pairwise time offset between each two cameras, and N is the corresponding number of visible 3D points, and Sij is the cost between each two cameras, which coded before the previous step, and B is the average baseline. Here, then after do that, here you're gonna have an ordering of cameras to add. And the last step, he trying to add camera one by one. So the new camera, he gonna try to insert in all the time slot of the previous processed cameras. And when he insert each slot, he gonna optimize the cost function for both the time offset and the 3D trajectory. But if this timeout set gonna change the ordering of the cameras, you're gonna drop that result. Finally, each time he gonna finally he gonna try use the timeout set with and 3D structure with the smallest cost. Yeah, so after that he trying to do a post processing, which is jointly optimize the odd value of 3D points and camera projection offset by the cost function, but only not changing the relative ordering of the cameras. And also he used the trajectory basis, which is DCT basis, similar, actually exactly the same of the previous method to present the structure of X, where X where is here, to present the X based on this basis and the coefficient, and put this back to the a cost function with so this new he trying to optimize this new function over the coefficients. Here is some experiment. First, he used motion capture data, which compare the reconstruction error with using the motion prior and with the DCT resampling, and compare with triangulation and spline resampling. And you can see the DCT have the best result, and also he compared the offset error for each camera. Okay, temporal error, you see, and also the reprojection error. Shows this is this after 3 is actually before the post processing, and this after 5 is with the post processing. They also do some real data experiment. Here is trying to reconstruct the black square of the checkboard, and also compare the this reconstruction error. And this is some experiment on the jump scenes, and in their result it shows the triangulation method gonna field to reconstruction on some faster motion part, but they have perfect, not perfect, they have a good reconstruction. Also their method in the low frame rate condition as good as the triangulation based on high frame rate case. And here is the second paper, third paper, which called self-expressed diction learning for dynamic 3D reconstruction. They trying to reconstruct the 3D dynamic structure without the knowledge of the sequencing information, which is a much difficult problem compared to the first, which he's supposed to know the sequencing information, and also using the unsynchronized video streams. And they try to pose this problem in terms of a self-expressed diction learning framework. Here is a principle. They suppose that based on observation, the F frame can be expressed by a linear combination of the nearby two frames, and this coefficient is between 0 to 1, and the sum to 1. Finally, build this width matrix. So each column they will force the coefficient corresponding itself to 0, since it shouldn't express by itself, and ideally we'll have value on the two neighboring frame and all the other is 0. Then he trying to optimize based on their cost function. The first term is the self-expressed arrow, and in this function, when you fix one variable blocks like x, it will be convex to the width, and if you set the width fixed, it will convex to x. And they can use alternative convex search to optimize this problem. The second term is trying to use the coefficient relation. He's trying to force this to be close to symmetric, since the weight is supposed to be symmetric on the position. Since the one nearby me, I should be his neighboring frames too. And the third term is trying to penalize distance between the neighboring frames in the same camera, since the sequencing of in the same camera is known. So they try to do this to smooth the trajectory. And this is some experiment based on the motion capture data. He's trying to do in different conditions, like low frame rate, add Gaussian noise, and different percent of missing point. Here in this graph, he's trying to represent the percent of points under some threshold arrow threshold. Like here is the percent of arrow under 20, the reconstruction arrow under 20 millimeter. They also do some real data experiment like this. Some people playing balls. And finally, we're going to introduce our method. We obviously call discrete Laplace operator estimation for dynamic 3D reconstruction. We trying to reconstruct by minimizing the second differential and first differential of the motion, which expressed in terms of the discrete Laplace operator. Also, we trying to recover global sequencing through a combination of dynamic time wrapping and spectral analysis of 3D motion, even in very extreme nonlinear motion and some repeating motion. The motivation of the problem is the dynamic 3D structure are going to have the adjacent information between them. In reverse, by knowing the adjacency information, we can build this discrete Laplace operator and use that to reconstruct the 3D strip. And the principle here, we see the 3D structure as a weighted directed graph, and each 3D shape at each frame is the vertex, and the edge is the vertex point to his neighboring frames, his adjacent frame, which ideally is the neighboring frame, and the weight is the adjacency between the frame. Here is the Laplace matrix, Laplace operator, which is also the Laplace matrix, equal to the odd degree matrix minus affinity matrix, adjacent matrix, which adjacent matrix is represent for each row of the adjacent matrix is the corresponding value of the width on the graph, and this odd degree matrix is the sum it's a diagonal matrix, and each value is the corresponding sum of the row of the adjacent matrix. And here I want to introduce the relationship between high-pass filter, self-expressed width, and the Laplace matrix. First, the high-pass filter, you can see it as a Laplacian operator that all the adjacent value is 1. And here, the out degree for each frame will be 2. And this is there is a Laplacian operator. And for our for the self-expressed width, it's you can see it as a Laplace operator, which all the false all degree is 1. Here, this identical matrix is equal to our all degree. But our Laplace matrix will not take those constraints. We set the all degree and adjacent value as using the based on the structure. And here is our optimization. Our cost function is based on 2 parts. First part is implied the Laplacian discrete Laplace operator, and is to minimize the second differential. And the second part is trying to minimize the first differential. I'm gonna introduce later. Here, since this Laplacian can be decomposed in this form, and D is D depends on the value of D. More important part is the proportional of each all degree. So we can set this to sum of those as a constant value, which here is 1. And it will be a cost function optimized over x, width, and d out, and it's a triple convex function. And here the second part is actually our definition for the Laplacian called Laplacian quadratic form for the directed graph. The original Laplace quadratic form is for the undirected graph, which equal to parallelize the difference between each 2 neighboring frames. And our definition here include another matrix called integrity, which actually is the integrity Laplace matrix. With here the integrity matrix is the sum of each column for the adjacent matrix, which means the sum of the value that point of the edges that point in these frames. So finally, our quadratic form equally to parallelize the distance between all the frames that how edges point out and also the edges point in. And this function also optimizes over x, width, and d, which is a triple convex function for them too. Finally, our object function is a triple convex function for x, width, and d. And during optimization, we're gonna set 2 of them to fix and optimize over another. First, the x can get from some initialization from based on triangulation method. And the first step, we're gonna set this d out value to the same value, and optimize over width, and then set the x and the width to constant and optimize the d out, and then set this to constant x, and finally this to some threshold. Here is our experiment with the motion capture data. Here is the result show our advantage on the low frame rate compared to the self-express method, and we have as is as good result when there is noise, and we have better when there are more missing point. And the most important part is when we try to randomly drop some frames, which make the distance for each frame, the adjacent frame, the distance to the adjacent frame different, which means the density of the frame is non-uniform. For the self-express, it will penalize the self-express error equally, but we have those dealt kind of like weighted the self-express based on their distance. You can see when randomly dropping more frame, our result is basically the same, but self-express gonna increase a lot. Here is some experiment on the real data. We use the dataset from CMU Panoptic Studio, which they're gonna have multiple synchronous camera and 2D observation of the joints, and also they have 3D structure of the motion based on their method with use synchronous video. And then we compare the result we choose full camera, and then somebody will make the observation is unsynchronized, and use our method to reconstruct. And we compare with their result. They are very close, and average distance between the joint is only 0.3 centimeters. And the graph on left, this is full image at the same time from different camera, and actually our observation only this one, the first one, which cannot observe the feet and some part of the leg, but we can we can successfully reconstruct this part, which show our robustity on the missing point. And another method we trying to do is trying to recover the global sequencing. We define this problem as a dimension reduction problem, which is see our 3D structure as a high dimension date with f date, and we're trying to reduce into one dimension and preserve the pairwise relation. Then we can simply compute the ordering by sort this one dimension structure. There are many. We use two dimension reduced method, which the spectral ranking preserve the pairwise similarity. Multi-dimension scaling preserve the pairwise distance. And the key point is how we compute this pairwise relation. And the most simple way is to compute based on the Euclidean distance, which will perfectly represent the relation when the motion is close to linear, but when the motion is extreme nonlinear, or the motion is a repeat. So the distance far away in time actually may be close in the space. So we're trying to compute the distance along the trajectory, which will better present this pairwise relationship. Here is our way to compute this. First, this trajectory we call arc distance between the frame in the same camera is easy, since we already know this sequencing information. But for the frame in different camera, it's kind of difficult. First, the method we use is first we use a version of time dynamic time wrapping to find the related position of these two frames. And when we find this, we can find this distance based on, for example, in this A and B, we know the neighboring frame is here, and we can plus the distance of this part and this trajectory distance along frame of around camera 1. This will compute all the pairwise distance between different cameras. And we do some experiment on the motion capture data. We also use some baseline method, which is trying to calculate the Hamiltonian path, which is the shortest path that passes through all the vertices only once. And if we have this path, we supposed to have a ordering. And you can see in linear motion, they all can recover the good good ordering. And our method, the X ultimate is better than X initial, which is the initial X based on triangulation method and our structure after optimization. For nonlinear motion, you can see only the spectra and MDX using ArcGIS compute the perfect ordering. And when there is a repeating motion, you can see most of the method will fail to compute a good ordering. Only the spectra and MDX using ArcGIS have a pretty good ordering. Finally, we're trying to take use of this method to reconstruction on some extreme condition. In this experiment is very sparse motion and also repeating. The idea here is when optimize the cost function over width, and when x and delta is fixed, this will basically optimize based on this pairwise distance. So we're thinking, since the Euclid distance cannot perfect represent the pairwise distance, but our one-dimension data from the ArcGIS is good. So we replace the one-dimension data, where here is f, replace the x, and trying to reconstruct the structure based on that method. And you can see here the self-express and our method using x is failed to reconstruct. They have a lot of error, and the width function is really far away from ground truth, which can represent the ordering. And use this f, we can reconstruct a much better structure, which error only 1 centimeter. And the width improve a lot, which more close to the ground truth, with supposed to only have value on this 4 column here, 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 and here. So for this extreme condition, our method improve a lot. And here's some future work. The future work basically is we'll try to analyze the reconstructability, which for now we seem have relation with the direction of the wearing and the motion. So, and also we'll do more experiment on real data. This is some reference, and thank you for listening. And any questions?